Alright, we've talked a little bit about the different states of matter. Now we're going to talk what happens when we mix different chemicals together, whether they be the same states of matter or different states of matter. It creates what we call solutions. And there's different types of solutions. There's a way we express concentrations. And then there's a lot that has to do with solubility that goes into solutions. Okay, just some terminology real quick then. Heterogeneous, homogeneous. Hopefully you're familiar with those terms by now. Heterogeneous means that everything looks different, so you can see the different parts. When you think of this one, think of like Italian salad dressing. If you look at a bottle of it, when you shake it up, you can see all the different pieces in there. And Italian salad dressing is also what we call a suspension or a mechanical mixture. So if you go and you grab the bottle out of your refrigerator right now, you'll look in there and you'll see different layers. You'll see like the seasonings on the bottom, then you'll see a liquid layer, then you'll see an oil layer at the top. Then if you shake it up, you create a solution, you create a mixture. And that's a mechanical mixture because you mechanically had to separate the pieces out and make it so it's a mixture. Then you pour it on your salad, you put it back in the fridge, come back a little bit later, well, you know it's separated again. So a mechanical mixture or suspension is one that is temporarily put into the suspension or into the solution form. Milk is another suspension. If you let your bottle of milk sit in the refrigerator untouched for a week or two, you're eventually going to notice different layers forming out. In fact, if you look on the side of the bottle, it says it's homogenized. That means it is mechanically put into a homogeneous mixture. So they whiz the milk way up so that it forms that suspension that actually lasts for a really long time. If you were to get fresh milk, it would separate out pretty quickly. Paint, same thing. That's why you had to get your can of paint shooken up before you can start painting, because the paint flakes all kind of settle to the bottom of the enamel, whatever the base is. Okay, then there's what we actually call a solution. So a solution is a homogeneous mixture of two or more substances. Homogeneous means that everything looks the same, so you can't see the different pieces. Think of purple flavored Kool-Aid. So you've got your purple molecules, you've got your sugar molecules, you've got your water. If you bring that cup of purple flavored Kool-Aid really close to your eyes and look very, very carefully, you still can't see the individual pieces. That's because it's a permanent solution. So those different parts are completely dissolved throughout and will not separate. By filtration, by time, it doesn't matter. And the reason those are so closely tied together and can't be separated by physical means is intermolecular forces. So those different parts are being held together by those intermolecular forces. In the case of purple flavored Kool-Aid, it's going to be the hydrogen bonds from the water and then from the sugar molecules, and then the dye molecules that are in there, the purple flavoring, it's going to have hydrogen bonds on it as well. So they're held together by those. The only way then to separate out those individual pieces would be to break the intermolecular forces, so somehow alter them so that they separate from each other. That would be like distillation or chromatography, which we've done in class. Separates them out based upon how polar or nonpolar they are. So not all solutions versus suspensions are that easy to break apart. Sometimes a suspension, it's really hard to tell that it's actually a suspension. That's because the individual particles that are floating around in there are so tiny that we can't necessarily pick them up with our eyes. And the way we can separate out a suspension from a homogeneous mixture or a solution is what's called the Tyndall effect. The Tyndall effect is the property where a particular solution will scatter light. Solutions will not actually scatter light, but suspensions or heterogeneous mixtures will scatter light. What that means is if we take two solutions, okay, we'll call this solution A and solution B, and we shine a light through them. So when light hits a heterogeneous mixture or suspension, the little particles in there will actually scatter light, which means the light is going to bounce off those tiny little particles. As a result, when that light shines through the glass, we would actually see that beam of light passing through the glass. And so you could see it inside there. If you've ever been camping and shined a flashlight in the smoke, smoke is a suspension because those particles are floating around the air, and you can see your flashlight beam floating through the smoke. That right there is the Tyndall effect. After it's been raining outside and it's a little bit foggy, you see the sun breaking through the clouds and see those beams coming down. It's also the Tyndall effect. So the light is being scattered by the particles that are in the air. However, a solution, if you were to shine your light through a solution, since those individual particles, those purple flavorings, those water molecules, or the sugar molecules are so small, the light will just pass right on by them without being scattered. And so when you shine a light through a solution, you don't actually see anything. You'll just see the light coming out the other end, but you will not see the light in between here. And so that's a way we can identify a solution versus a suspension. Okay, last bit of terminology, a solvent versus a solute. So a solvent is a substance that is more plentiful in a solution. So whatever there's more of, that's the solvent. The solvent is what does the dissolving. So in the case of sugar and water, water would be your solvent. The solute is the substance that is dissolved inside of the solution, and it's whatever there's less of. More often than not, water tends to be the solvent just because that's usually what there's more of. Not always the case though. Just think of the solvent as whatever there is more of. So if you're unsure which one is the solvent, just look at the quantities. Whichever one has the higher quantity, hey, that's your solvent. So a saturated solution is one where a solvent has dissolved the maximum amount of a particular type of solute. And, this is all temperature dependent. It's also dependent upon the solute and the solvent. So water might be able to dissolve, let's say we have a liter of water, it might be able to dissolve 10 grams of salt, but 20 grams of sugar at a particular temperature. If you warm it up, it's going to be able to dissolve more or possibly less, depending upon what the solute is. And as it turns out, saturation is actually just a form of equilibrium. We're going to go into detail on the calculations involved with that. So if we've got a particular solution that is saturated, that means we're going to have our maximum amount of solute up here, and then we're going to have a little bit of solute undissolved at the bottom. And we would see that just as little bitty chunks down here. And what that means is if there is some solute at the bottom, that does not mean super saturated. Okay, because it's not dissolved, it's undissolved at the bottom. But that undissolved part down there is not going to stay undissolved. In fact, it's going to start dissolving. But when it dissolves, that's going to cause some of the solute that's in the solution to undissolve. And so we wind up with this equilibrium. So this chunk down at the bottom is not going to stay the same chunk the entire time. It's going to dissolve, but as it dissolves, other stuff is going to precipitate out. And we set up this equilibrium, dynamic equilibrium, where overall the concentration out here is going to stay the same. Yeah, don't worry, we're going to spend an entire lecture talking about just that and how to do the equilibrium concentrations with it. Finally, I'm going to breeze through the different types of solutions. The most common one that we think about is a liquid-solid solution, not the only type. In fact, every state of matter has different combinations to create different solutions. I'm going to buzz through these pretty quickly, but notice there's a lot of information on the slides. I'll just leave that up to you to read. So the first one is a liquid-liquid solution. This is when we dissolve two miscible liquids in each other. Miscible, liquids that are soluble in each other. So oil and water would be immiscible. That would not be a liquid-liquid solution. When we dissolve some water with some methanol or some ethanol or some other liquid, that would be a liquid-liquid solution. So an example of an immiscible liquid would be water with hexanol. So hexanol does have a hydrogen bonding group right here, but it's also got this huge nonpolar carbon chain. So that larger nonpolar carbon chain is going to make it so that the water molecules actually have a stronger attraction for each other than they do with the hexanol. So as a result, only a small amount of hexanol will actually dissolve in water. The rest of them are going to stay bonded to each other. Hexanol would actually be miscible with something like hexane. So hexane is just a long carbon chain group, and as you can see, this is only going to have London dispersion forces, and since we've got a long nonpolar group and a long nonpolar group, these two would actually be miscible because they would have a higher attraction than water would for that guy right there. Finally, the most popular would be solid liquid. So this is when we take our salt and we dissolve it in water. We take sugar and dissolve it in water. The most common one that we've seen from kindergarten on up. So most ionic compounds dissolve in polar solvents. That would be an ion dipole. Polar solid, so glucose, that's sugar, dissolve in polar solvents. And that's because they're going to have hydrogen bonds or dipole-dipole. Also, nonpolar solids, like mothballs, dissolve in nonpolar solvents. Now we know from the solubility rules that not all ionic compounds are soluble in water, and that's because the ion-ion attraction for those particular compounds is stronger than the ion dipole between water and the ions. There's also gas-liquid solutions. So carbonated drinks, any soda pop is water with carbon dioxide dissolved in it that forms an aqueous form of carbonic acid. That's what gives us kind of tingle on our tongue. So this would be an example of a gas dissolved inside of a liquid. Oxygen can also dissolve in water. That's what keeps fish alive. If there wasn't oxygen in water, their little gills wouldn't be able to breathe anything and they would die. So the fish of the world, thank you, oxygen, for being soluble in water. And then there's gas solutions. And as it turns out, gases are infinitely soluble in one another. So there is no such thing as an insoluble gas in one particular gas. Air would be an example of a gas solution. The air we breathe, is composed of nitrogen, oxygen, carbon dioxide, water vapor. There's a little bit of argon mixed in there, helium, hydrogen. So all those different gases infinitely soluble in each other. If we were to pump more and more nitrogen into the air, it wouldn't necessarily create a supersaturated solution or even a saturated solution where the excess nitrogen would start to fall out and precipitate. No, they're just going to keep mixing together as long as we put them together. Here's a piece of trivia. So, in a gas-gas solution like air, what is the solvent and what is the solute? If you said nitrogen was the solvent, you are absolutely correct. Nitrogen composes 79% of our air. Since it is the most abundant thing in the air, that would make it the solvent. And everything else, the oxygen, the CO2, the water vapor, and everything else, would be the solutes. Gases can also dissolve inside of solids. So for example, hydrogen gas can occupy the spaces between some metal atoms such as iron and palladium, and so they can actually dissolve hydrogen gas inside of palladium. This is actually one way that they store hydrogen gas. Hydrogen gas is so stinking small that just trying to pressurize it inside of a bottle, it'll all leak out. However, if we dissolve it in some solid palladium, we can have it there and we can actually store it there. This can also create trouble, though, in like iron pipelines. So oil that they run through iron pipes, hydrogen gas that's in the oil will actually dissolve into those iron pipes and cause those hydrogen gas to then form together and push apart the iron molecules. And as a result, it will cause leaks in the iron pipe. As a result, iron pipelines, before they start piping oil down them, they'll remove as much hydrogen gas as they possibly can from it. Otherwise, it'll cause it to spring leaks down the road. And finally, solid-solid solutions. So these are formed by melting, mixing, and solidifying solids together. So steel would be an example of a solid-solid solution, and we call it an alloy. So an alloy is a solid-solid solution of metals. So what they do is they take metals, or in this case a metal, non-metal, and mix them together to create new solid properties. So steel, different kinds, they take iron and then they put carbon in between there to fill in those spaces between the iron atoms. Rather than leaving those large gaps that will cause it to be more brittle, by filling in those spaces with carbon, creates a more solid structure. And this is an interstitial alloy because we're using carbon in between the spaces. So we're not actually changing the structure of the iron, we're just filling in the gaps with some carbon. So pure iron lacks directional bonds. That means the iron atoms that are sitting next to each other can't really stick together very well, and so it's really easy as a result to bend and twist and even tear iron. However, when we use carbon in between those gaps, it causes there to be bonds in between the different layers and different sections of iron atoms and the carbon atoms, and so it holds together and winds up being much, much stronger than just regular iron. And since those carbon atoms just fill in the gaps that were already in the iron, it doesn't actually change the volume of the iron by adding copper into it. So as a result, it winds up being much, much denser because we're adding more mass in the same amount of volume. And then there's also substitutional alloys. These are different because we're not filling in the gaps like we were with the steel. Instead, we actually swap out a particular metal atom for another one. So an example would be brass. Brass is an alloy between copper and zinc. And you can see here that we have zinc and then copper's mixed in. And so they're not really filling in the spaces. Instead of being a complete section of copper or zinc, we've just swapped out some of the zincs with coppers. These alloys remain malleable and ductile, but they actually have different properties than zinc or copper. So it's not just a combination of zinc and copper properties, it's now brass properties, so completely different than their two parents. Discovery of new alloys with new properties is what created new civilizations throughout history as well. Can you imagine playing Age of Empires without alloys? It'd be a really boring game. So thank you, alloys, for giving us cool video games.